at the moment, I think we're at the assistance stage, and we probably will be there for a long time, because I think we always need human approval. And just to tell you and why I think this will be. So if we train these computer vision algorithms, we do it with massive amounts of data, whatever we have. So they can treat all the standard cases very well. When you look at the education of a radiologist, he's not trained on looking like, here are 3 million images, look at them, and then you're done. No, he's trained with edge cases.
Namaskar and welcome to another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified. This podcast is brought to you by IITM Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global is our platform to take everything IIT Madras and India at large to the world. Our thinking, our philosophy, our startups, our teaching, our research. Learn more about what IITM Global is up to in the link in the description below. We're going to talk about a cross-cutting technology that cuts across multiple engineering disciplines. A science that evolved several decades ago and has now matured to where you and I are today beneficiaries of all of the research and development that has gone on for the last several decades. Computer vision. To help us understand and parse this very exciting space, I have an absolute expert of this domain, Professor Horst Bischof from TU Graz in Austria. Horst has been immersed in this field for as long as the field has been relevant and more, and it's a delight and honor to be hosting you, Horst. Welcome to the podcast.
Yeah, welcome. I'm also happy to be here and talk a little bit about my research field.
Thank you. You grew up in Austria and you took to computer science in the mid to early 80s. Tell us a little bit about what it was like to be a college student studying computer science in that time.
Well, actually, I was born in Switzerland, but then soon after that moved to Austria, small regional part, small village, like about 1,000 people. From there, I went then on to high school, and this was sort of the first time when I get into touch with computers. At that time, there was sort of an extra lecture offered in high school, and I thought, why not taking that? Besides that, I did also the other things like math Olympiads, physics Olympiads, chemistry and blood. I was just interested in science, so one would say, but also this computer thing. Then I thought, well, I buy a computer for myself. Commodore 64 was at that time. So unfortunately, I sold it later because I had to buy a new one. But this, and this is how I somehow stumbled into computer science in high school. Yeah.
And college in those days at TU, fine, where you studied computer science. What was the environment there like?
From high school, I sort of moved to TU Vienna, which is the Vienna capital of Austria. Main reason for going to Vienna was it was far away from home.
Well, no different from many Indian students thinking.
Well, unlike Austrians usually stay where they are born, so this is sort of a difference. Yeah, and then of course I came up to the decision computer science was the thing, and of course at that time it was, standard things like programming, of course, a lot of programming, but also like the basics, which I think is important, math and these things. I was always, during my studies, always inclined towards a little bit mathier things. So whenever there was a choice, I was choosing more towards the math side. And then I somehow came across artificial intelligence, neural networks at that time. Well, actually machine learning before, and then somehow stumbled into neural networks. I was living, sharing an apartment with a guy from biology, and he told me at that time, in biology, we have really problem, which is protein folding. How do we determine from this 1D structure of proteins the 3D structure? I said, this is an interesting problem. So I thought, well, let's gonna solve it. Of course, this is. And then I did some work in protein. So I went to some biology classes just to learn the basics, and I tried to develop a software using neural networks, how proteins would fold. And this is something that last year earned a Nobel Prize.
Yes, yes. Wow.
So
almost 40 years ago.
yeah. Well, but this is the thing is curiosity. So of course it was not feasible at that time. Actually, it stopped then because the databases were not available in Austria at that time for doing this learning thing. But the idea was there, and this brought me then this was then towards the end of my study, the master thesis, and I came another institute which was at another university. They're dealing with forestry, and they wanted to know the tree species from aerial photographs. And so I wrote a neural network to determine the tree species from aerial photograph. And this is basically how I entered research, and from there was sort of just small steps going forward. Yeah.
Oh, so I think that laid the foundation for you to become interested in images and computer vision. So how did that get?
Yeah. Well, actually before, I was more interested really in the machine learning side. I wanted to do, and images were always sort of an application for my machine learning thing. But of course, then the more and more I did was that maybe I should better understand what's behind these images and what else one can do. And so this is how I sort of slowly entered the imaging field. Then a new institute in Vienna was formed, where I became then assistant professor on image processing. And then, of course, one has to teach a little bit, and one gets to deeper into the subject. But I always kept sort of this link, learning plus images. And then over the time, images won, but nowadays it's the machine learning is back again. So just what an accident.
Unbelievable that you started where we are today, right?
Yeah.
Before we go very far, let's just understand what is computer vision. Help our listeners understand what is this broad field, what's under the hood.
Well, if you say it in very broad terms, is basically computer vision is given an image or given a movie, tell a story about it.
Okay.
So every one of us, I show you an image, you can immediately talk 3 minutes about this image, because we understand what's in there, what are the objects, how they relate to each other. And exactly this is the whole goal of computer vision. Given images, given movies, sort of completely understand what is going on there. But of course, this is sort of the holy grail or the goal of the whole field. Now, and of course, in order to do that, you have to do many subfields. First of all, you have to understand how images are created. This is a big thing, and usually when we say images, we think about standard optical RGB images.
Sure.
But of course, there is a rich source of other types of images. Might it be other wavelengths like infrared, but then there are completely other different types where images appear. Think of medical images, MR, CT. This is a completely different scanning technologies. At the end, it ends up with an image, either 2D, 3D, maybe 4D. You have a sequence of images, then we talk about movies. You can talk about a sequence of 3D volumes. You have another things when you have 3D sensors that give you already 3D data. So this is even the input side is very, very, very rich and large. And from that, you usually, and in the standard way of doing that, you would start off, preparing, improving the images, removing noise, getting rid of the thing, and then starting along this pipeline to understand these images, like forming segments, maybe object parts up to objects, till finally you come to recognition stages. What is now done is some of these parts are using neural networks are sort of jumped over. You go directly from the image to the interpretation. But, and this is probably one of the advices I would still give young students, well, I still give young students in my lectures, say you need to understand also what's behind the hood. It's not just applying a neural network. Mm-hmm. It helps you in order to get really good results. What is the nature about that?
You said it so eloquently. Yeah. Tell a story about an image. Yeah. If a human being was to do it, we have sort of an intuitive way of focusing on the important things in the image. Mm-hmm. How do you train a computer program to realize the level of importance, or is that still a work in progress?
Yeah, this is probably one of the utmost importance. When we as humans look at an image, we see immediately what is important, what is not important. The problem with computer vision and image processing is always it's such a huge amount of data. And of course, taking every pixel sort of and playing around with that simply would cost you too much time. So the one of the things, and humans are just perfect in that, getting rid of all the data you don't want and then concentrate on those parts that are really important for the task at hand. Yeah. It's also task oriented. One image in different contexts might be interpreted completely differently, or other things are important. So this is, it's not only about, what's in the image, it's also about your context, what you want to achieve with that, where you want to go with that.
One of the earliest victories of deep learning actually came from computer vision, sure. Handwritten numeral recognition and handwritten character recognition. Tell us a little bit about what caused that victory and what did it mean for the deep learning community at large? Yeah,
so if you look sort of, and this is one of my advantages, I followed somehow the history of that thing. So this character recognition work by Jan LeCun, also like so basically Jan and we met when we were sort of students at conferences. So basically, it was applying neural networks to character recognition. The advantage there, and why it worked to some extent, there was enough data for doing that, so you could get reasonable results which were usable. For a long time, our real problem in all these things was we didn't have enough data to train the things. And then later, when Karpathy came along with this AlexNet, again, the story is like in computer vision, we had our benchmark data sets, like this ImageNet 101 and others. And people, and this is the nice thing about benchmark data sets, like at every conference, like this important CVPR, ICCVs, and so on, people are showing the results of their algorithm on the database. And if you would look the last years before this AlexNet came around, the improvements were like 0.5%, 1%. So okay-ish, this was, I would call it engineering successes. And then when this AlexNet was around, they presented the results. It was a jump more than 10%. So, and this is significant, sure. 10% is, and everybody then, of course, was looking at how was that possible to get this 10%? And this was a deep neural network. And then from that, the whole thing took off. Everybody saying, well, let's try this on my problem. And basically, they were using AlexNet and variations of that on their problem. Then the next year, what they did is they made the AlexNets just bigger. The data was enough to train, so you got the even improvement. And so this is how the race started. getting more data, getting better models, getting better results. So this, of course, from a scientific point of view, would say, well, this is, what the hell. And also what is interesting, and I kept telling and I remember that when a student came to my office and said, look, I have seen this great work coming out there. Should we discuss it? Should we go into that? And I was explaining to him, yeah, I know they are using backprop, blah, 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 blah. How do you know? I said, well, I did this 20 years before. The difference, and this is the lesson learned, the algorithms are the same. Of course, there is improvement here and there, but overall, it's still somewhat the same algorithms, but data is there and computing is there. So now we can scale these things. All these things we have dreamed of 20 years ago now seem to work. So the ideas were not too bad.
Wonderful. Before we go very far technically,
Yeah.
let's take a step back and help our students understand the pipeline. How does one build a deep learning model for computer vision? Where do we start and what are the different steps involved?
Well, I think the most important thing whenever you start something is define the problem properly. What problem you want to solve, no matter what you do later. So once you have that, the next question is, and when you use deep learning, as I said, you need a lot of data. The question is, where do I get the data from? It might be that you say, well, there is a database available I can use, or you have to create your own database. This might be really tedious because creating a database means you need someone to label the images. Or, this is the more interesting thing, is to come up with methods to auto-label these images via some other sources of information. So data is the next thing that must be clear. And if you want to use deep learning, it needs to be massive. So this is, so don't play around with 3 images using deep learning. This will bring you nowhere. So data, and once you have that, you need to decide on the architecture of that network. There are sort of various prototype architectures around. Of course, then once you have decided for a certain prototype architecture, you feel around a lot of with parameter size and how many layers, how deep, how many units I use in what layer, or what other components I use. The nice thing nowadays is you have a lot of software, so this is more like plug and play. You can easily do that. Then you need the compute. Of course, you need to process the large data, so you need somehow someone to pay you to compute.
Sure.
And then another important thing is of course testing your applications in sort of the world. So this would be sort of the standard just deep learning thing. Usually what you find out, what people are doing and the successful applications, they are designing different modules with different architectures of different neural networks. So you go deeper into the problem, make it more problem specific. So if it's a 3D model, you do something different when it's just 2D. So yeah.
It's only fair to ask, what was computer vision like before deep learning and machine learning? I'm sure there were serious efforts. What were some of those efforts that actually resulted in good?
Well, actually, if you look around, there are still many systems using conventional, as you would
Heuristic based.
Yeah. So basically, the thing was, again, defining the problem was always there.
Sure.
The next step was sort of to design a pre-processing stage. Usually this involves a lot of filters. You were hand designing filters or using customized filters like for edge detection, for whatever. Next step, you would use some segmentation algorithms. Again, hundreds of segmentation algorithms to choose from, and depending on what goal you have. From that, you would go on towards more interpretation, like deriving sort of meta-knowledge from that images, going towards the recognition. In recognition, there has been always a lot of learning and machine learning involved.
Okay.
Of course, not always neural networks. sometimes decision trees, and many of these other machine learning algorithms. All of them have been used in computer vision. This makes it feel so nice because you can, whatever algorithm you can use in computer vision. This is this is the interesting thing. I remember I once, sorry for this detour, but I once I was teaching a class, mathematics for computer vision.
Okay.
And I went into the class and said to the students, there is no mathematics that cannot be used for computer vision. Students sit there and looked at me, said, okay, professor. But there were also a few math students there. They said, Professor, sorry, we don't believe you. And I said, well, let's make an experiment. At the end of every lecture, you tell me a mathematical property, problem, whatever, and then the beginning of the next lecture, I tell you how it's used in computer vision. This made me sweat the whole lecture because they came up with the weirdest mathematical concepts. It took me then half a week just to understand what this mathematical concept was, but at the end I could show the relation to computer vision. So I won this challenge.
That's fantastic. I think you're right in that the end goals are so diverse.
Yeah.
Let's talk about the end goals. You already talked of recognition, classification. What are all the different ideas that are being experimented? What are all the different possibilities that you can do with images now?
Well, first of all, you can do almost anything with images, and this is also what so fascinates me about the field. You can apply computer vision almost everywhere. And if I look back in these projects I have done in history, first of all, if I look at now at my university, I have published in each and every field our university has a paper. I have chemistry publications because you can use vision in chemistry. I have physics publications because we used it for particle tracking in high energy physics. I have mechanical engineering publications and so on and so forth. So computer vision can be used almost everywhere. Even some more strange things. I had students going to Nepal because there are these big honeybees. These are sort of bees of that size. And I worked together with a biologist, and he was interested in the wave behavior of these honeybees. These bees, what they do is when a wasp approach the thing, they are making this wave like humans make the Laola wave in the stadium.
Yeah.
They do this for defending thing. And the biologist was telling me, there are only two species in the world that make these waves. The one is the human, the other one is the honeybee. So he wants to understand it. So students went there, took cameras with them to Nepal because there are these things. And we started with computer vision, how this wave propagates along the nest. Another story is when I was fresh in Graz, someone from theology found me. And he said, Professor Bischof, I want to do a project with you. Usually you would say, theology and computer vision.
But theology and Bischof are not
far
far away.
And I said, well, come across. Then he said, well, our institute is studying religious symbols in movies, where they appear. I would need a software to help me to detect these religious symbols. And so this is, we did a project with him. And then I went to a conference and I said to a colleague and said, I'm probably the only computer vision guy in the world who works with theologists. And he looked at me and says, well, your name.
Absolutely the story. Right? That's, I think, that talks to the breadth of disciplines that this field has already touched and is even more likely to touch and change. I like I started to say in my introduction, this is a field which is already on my cameras with simple things as face recognition and everything else. So it's not future promise we're talking about. It's here and now in many ways.
But what's so fascinating for me, and this I keep telling my students, when I started that field, it was a complete obscure part of computer science. It was not in the center of computer science. When I started that, people say, you can do that, play around with that. There were only two applications. The one was medical, and the other one was satellite images, because the instruments are so expensive, so you could really afford to do that. Now I followed that field from sort of an obscure field of computer science to the heart, to the center of it. Every one of us is carrying a computer vision workstation with them, the mobile phone. You know, you have cameras, you have a lot of image processing going on there. The images look nice because they are processed there. This is computer vision, and this is really nice to see that development.
Sure. And so let's talk about the different tasks that underlie the basic idea, right? How does a face get recognized? Let's talk about what does the algorithm rely on for image recognition, pattern recognition in there.
So I give you two answers to that. So if you look at face recognition, again, a nice thing, I kept telling in my lectures, face recognition. So when sort of in the 90s or so, when this thing started, this is a difficult problem, and we will probably succeed when the images are nice and mugshots and these things. No, it's everywhere. So don't believe the professors, what they say in the lectures. Challenge them. I think this is another important message for the students listening to this talk. No, but at that time we believed we should extract features of faces and measure like eye lengths and these things. Nowadays, these algorithms based on machine learning and mainly deep learning, but it has been before, and I think face recognition was a particular nice example that pioneered sort of this learning-based computer vision, because at that time there were already a lot of databases, and so a lot of machine learning algorithms were tried out on face images. And it turned out that it's not the individual feature you recognize a face, it's more the holistic appearance of the face. It's sort of how the composition is of the different parts. It's not like your left eyebrow determines your name, but it's more really the holistic thing. So all these approaches that were based on extracting individual features and then classifying far fall below these more holistic things. And this is exactly what also these deep learning algorithms do. They look more holistically on the whole image and determine which parts are sort of together.
Let's talk about some tangible applications that are here and now and possibly in the future. You talked about healthcare.
Yeah.
Let's talk about what is computer vision already doing there, and what are some promise? What is the promise that it holds?
Yeah. So if you look at healthcare, first of all, computer vision has been very long in healthcare, starting with the image generation. If you look at an MR or CT machine that give you the 3D volumes, there is a whole lot of computer vision going on there just to get the images, the 3D volumes. Basically, image reconstruction, you have to solve inverse problems, involves quite some sort of optimization research. And still, there is a lot of research still going on there, because you want to minimize the number of slices you take, because you want to minimize the radiation or the time of imaging. And then you need better reconstruction algorithms. So there is a lot of work going on there. But the other side is the interpretation side. Now this is mainly used wherever an image comes out, you can use computer vision to sort of detect either cancer or other things you're interested in. Particular examples that sort of work really well is like melanoma detection on the skin, or like the breast imaging and detect cancer on this type of images. And there you usually find that these algorithms are performing better than sort of standard doctors interpreting these images. And the reason is also clear, because they simply have seen already much more images for their training than a usual doctor would see. And of course, and this is what we know from deep learning, whenever you have enough data you can train on, you get better results. And so wherever you generate lots and lots and lots of images, then this type of algorithms are really useful and will be useful also in the future. And we're sort of exploring. There is a nice book by Eric Topol called Deep Medicine, which sort of explores all medical stages, how machine learning can be used and help in sort of getting better results. And so of course, the obvious thing is radiology, but there are many more, like you could even think about sort of surgery and this type of things. Also, surgery, computer vision can be a lot of help in giving you live information during your surgery. This then goes on to this more augmented reality type thing. So combining computer vision with computer graphics, and everywhere at the heart, there is a computer vision algorithm in order to do that.
Are we at a point where this is assisting a radiologist, or is it likely that the radiologist would be replaced?
At the moment, I think we're at the assistance stage, and we probably will be there for a long time, because I think we always need human approval. And just to tell you and why I think this will be. So if we train these computer vision algorithms, we do it with massive amounts of data, whatever we have. So they can treat all the standard cases very well. When you look at the education of a radiologist, he's not trained on looking like, here are 3 million images, look at them, and then you're done. No, he's trained with edge cases.
Yes.
And say, look, this doesn't look like cancer, but here this small spot, here that small spot, this makes it appear as a cancer. This is the training that a radiologist gets. So my vision on that is that the standard cases will be treated with computer vision technology, and these edge cases where a radiologist has been trained on will be still treated by him. So he will get the suggestion of the computer vision. I will say, no cancer. He said, but look, here we have this edge case, and here we may overrule the decision.
I'm going to ask, as a thoroughbred mechanical engineer with very little backing, is there a neural net architecture that likes to be trained on edge cases rather than the run-of-the-mill large amount?
This is exactly what is sort of one of the research questions we are dealing with. So as I said, currently we are sort of just throwing massive amounts of data to these things, and it brought us a very way. But now things are sort of slowing down. So the question, and this is a big research question, how do we pedagogically teach neural networks, curriculum learning, like we as teachers, we also not say, look, here's the library, and then that we teach them in a very pedagogical way. We think what concept first, what is the next concept. This is not by far developed in neural networks at all. So, but it's a very interesting research question, how to sort of build the knowledge, and then this would reduce, of course, the amounts of data we need for training, would reduce the amount of burden we have in computing, and would in the end result in better neural networks.
Another problem with neural nets broadly is explainability of the results. Where is computer vision there? Or are there paradigms that are more explainable than others?
When you look at explainability of computer vision, I have two answers to that. The first answer is, well, even a human cannot explain why he recognizes a certain thing. Of course, you always have post-explanation, but when you look at a cat, you say, well, this is. You immediately say this is a cat. Then when I ask you, why did you recognize this as a cat, you come up with an explanation. But this is not how the brain recognizes the cat, because for some of these things we can understand that in the
certainly brain. Not pixel by pixel.
Yeah. So it's sort of a post hoc explanation that we usually do. So I think certain parts of computer vision will be never explainable, as it is for humans, simply because we don't have the words for the concepts that happening with these low-level features. We of course we say this is edge-like, but we simply don't have the vocabulary for explaining. For the higher level ones, of course, we have. But what we humans are good at, and this goes into the explainability question, is once we have the result, we can verify it top down, and this is basically the explanation you're giving. It's a cat because it has 4 legs and a tail and blah blah blah. But this is your top-down verification of the bottom-up vision result. Again, a very interesting research question. We are not even, I don't know how to solve that,
Very interesting.
Yeah.
Let's switch to another application that's again here and now, automotive engineering.
Oh, yeah.
Self-driving
Yeah,
cars.
sure.
And, what made that possible? And what are the sort of the technology elements that excite you even today?
Yeah, so autonomous driving, again, has been for a long time around. So there are sort of, like if you look at the NAFLAF experiment, I think this was in the beginning of the 90s at Carnegie Mellon University, where they equipped basically a bus because they needed big computers, so it had to be a bus. And 2 cameras, and basically they trained the neural network to do lane following, what it would now call it. And it drove, of course, But at that time, the whole thing started, and it's as many fields ups and downs. Then it really took off with this challenge where they drove the desert challenge, where then the Google car won basically the challenge. And now if you look at it, it's now become more and more an engineering way of doing that. So if you look at the successful autonomous cars now out there, they don't have just cameras. They have lidars, they have radars, and other sensors. And by using all this sensory information, and of course images, and they can sort of build a reasonable world model and drive, as you see in San Francisco and other cities, sure, quite successful. Of course, the problem is not solved at all. Me coming now to India, let's say, seeing the traffic here, as I said, the problem is solved once we have an autonomous robot fleet driving here in India autonomously through the city. But then this problem is definitely solved.
And we humans do it all the time.
Yeah. No, but the thing is, so now why we have these different sensors there? So the Elon Musk says, well, human has 2 eyes, he should drive just with cameras. Yes, that's true, but we have a lot of extra knowledge around. These additional sensors give us basically, and this is now the engineer speaking in me, not the scientist, saying, well, they are here, why not use it? Because they give you this reliability you really want to have. Because as I always say, this autonomous driving has two things. One is the engineering part, where we can sort of say we can now safer drive than an average human, producing less errors, less fatalities. I think this is a stage we already have reached to some extent. The other part is when, and this happens also now and will happen in the future, when such a robot car kills a human, it will be in the newspaper. And this is then sort of the social challenge you also have to solve. Because, if you read in the newspaper, robot car kills child somewhere, this is not acceptable for us. So we couldn't argue, but statistically we saved so and so. This is not of interest to anyone. So in order to be really completely autonomous, we need to much go beyond the human capabilities, so that we have basically knowings, and this is still a long way to go to.
Seems like our demands of a machine are far more than our demands of a human driver.
Yeah, definitely. Because, and the reason is also clear, because we all say, this machine then will always make the same error. The humans sometimes is, more awake, sometimes less awake. So it differs, our interpretation, what a human does is different what a machine does. Because machine, and we have learned a machine is a perfect thing. It always does the same thing. And this is the same thing we believe of an autonomous car. It always does the same thing.
One last question on the autonomous driving part. The Carnegie Mellon experiment had assistance from the road, meaning the road had certain. Today, a Tesla requires no assistance from the road. Whatever it requires information-wise is built into the vehicle. What made this switch possible? And also, is it a good idea to have some assistance from the road to make the whole system more robust?
Again, if you're an engineer, you say, of course, I take any assistance I can get from everywhere. But you need at least certain, sometimes this assistance from the road might be not there, I mean, you don't want to stop and wait there for an hour till it comes back. This is not the thing you want. So you need at least a certain autonomy over time so that you can follow that. And we haven't even talked, now about weather and all these things that also happen, Coming from Austria, we have snow, and then driving in snow is again different. And here you have monsoon. Driving in heavy rain is a completely different story than sort of sunny, nice weather.
That's a great segue to what I had in mind next. Computer vision seems to have developed a certain element of robustness that is lacking, or that is characteristic of hard engineering.
Yeah.
You said, images can be recognized in multiple environments, right? What is under the hood to make this robustness one of the features of computer vision algorithms?
Well, I think we have learned, because an image is a rich source of information. There is, gigapixel, this is a lot of information. And what we have learned is how to leverage this information also for robustness. When we talk about engineering, of course, we have learned to use different sensors to integrate it. Human does that also, we are not just eyes. We have ears, we have a skin, we have other senses, we hear, and so on. The marvelous thing about the human is he integrates all this information. Also, if you look at computer vision, for example, 3D, how do you recover 3D from images? A classical computer vision problem.
Sure.
You have on the one hand 2 eyes, stereo, fine. But I can also do 3D with one eye closed because I have so many other cues. I know approximately the size of your face. This gives me a cue how far you are. I have shading algorithms, the light comes from that side, so I can roughly reconstruct that thing. And the human automatically uses all these different sources of information seamlessly without thinking to create a robust algorithm that would work when the light is turned off and so on. And this is exactly what we need to do in order to get systems robust.
Very interesting. Briefly, let's talk about what are the other applications of computer vision that either you worked on or you've seen colleagues work on from biology and other spaces.
As I said before, there is no field where computer vision cannot be applied. But if you will look at more the mass type of things, of course, there is a part is surveillance from biometrics, face recognition to following humans, doing surveillance in airports and all these things. We talked already about autonomous driving, which is sort of a big part. We have the medical thing. Of course, we have a lot of remote sensing, satellite, aerial imaging, all of these things, images applied. And of course, we have all the internet, social media type things. These are images that are used, and then we have sort of, if we move on to more the graphic sides, we have augmented reality, which is computer vision combined with computer graphics. Going on to virtual reality, 3D reconstruction. How do we get all the 3D models? We have applications in civil engineering, now sort of new projects coming apart, like complete surveillance of a building when it's built, sort of to check that. Then we see now also autonomous flying, drones, a big application area. and many, many, many more.
Very exciting time. The traditional computer vision training happened in computer science departments. That was
Yeah.
your beginning as well. If a young student today wants to take to computer vision, where do you suggest they start? What are some initial starting points, and what are possible branches that they can diversify into?
Well, the nice thing about computer vision is you can come from at least 3 to 4 fields. The one thing is the computer science path. You know, you learn about algorithms and programming and so on, and then build vision systems. The other part, and a lot of computer vision people come from mathematics, because computer vision is very rich in mathematics. So you can develop mathematical, if you have a good mathematical understanding, you can develop algorithms for computer vision, and then you do a little bit of the programming there. The other thing where people come from is electrical engineering. More from the sensor side, and then to developing and the signal processing side, that is more home to electrical engineering. So in all these 3 things, you see people doing computer vision there. This would be sort of the traditional ways of doing.
Let's take, if a postgraduate student in mathematics wants to meander into computer vision, what are some things you would advise that person to do along the way of completing their master's in math?
Actually, quite a few PhDs that did the math and then joined me for computer vision thing. Of course, I would recommend take 1 or 2 basic courses just to get the basics, to get the vocabulary, what image is about, and then look for a project in maths that is related to computer vision, and there are plenty of those.
At the end of the day, an image is just a matrix.
Yeah.
So you start with that idea.
Well, but when I was teaching in front of math students computer vision, they later came to me and said, wow, gosh, now I understand how I can use these abstract mathematical concepts. This is the advantage of computer vision. You can always see the result in terms of images. This helps you in really understanding. Even the mathematicians that are trained to work on abstract concepts, imaging and showing results helps. You can sort of, if you have a complex algorithm, you can show images in between to see what's going on, and
Absolutely. I work in fluid dynamics.
Yeah, sure.
And we're all the time converting the velocity fields to images to convey what's on our minds. Beyond math, what would say, if a mechanical engineering student wants to sort of, has an interest and wants to develop applications, would it be sufficient if they took some basic foundational courses in computer vision and then start working on applications thereof?
Yeah, definitely. I think, nowadays the time is right because all the tools are there, The mechanical student would much deeper understand the problem. And as I said before, the first step is always understand the problem. What do you want to solve? So the mechanical engineering student already has done, knows this part. Of course, he needs then to have the algorithms and the things around, but he can get much faster to that once he understands sort of the basic building blocks. And this is now, as I said, nowadays much easier than it used at my time, because software is around which we can plug together, play a little bit and get a feeling what these things are doing. But still, a little bit of basic education you need, just not to do random search in that.
That's a good point. Again, I work a little bit in computer vision myself, because I work in human crowd motion. So we want to detect individuals and detect pathways. My students ended up using what was already available, YOLO and toolboxes like that. Where would you say those toolboxes are good, and where would you say one needs to develop one's own algorithms? I'm presuming these toolboxes have matured quite a bit along the way.
I think these toolboxes are always good in order to get started, in order to give you also sort of a thing what can be achieved with state of the art, And then you might say, well, this standard thing, 90%. This is sufficient for my task. No, they fail here and here. And then of course, you need to develop specific algorithms in order to solve these cases. But then you can go to a computer vision specialist and say, look, these are my problems. And you can much better explain to him the problems you really have. And yeah, actually, I also worked for some time in this crowd motion things. We have been using optical flow a lot, in order to think, because we have been working in optical flow. And so we're using basically these algorithms we developed there also for crowd motion algorithm.
Sure, wonderful. I think India is a country of crowds.
Oh yeah. In Austria, we had to use students when they came out of the lecture rooms just to get enough images of crowds.
I don't have that problem.
Yeah, that's true.
So let's talk about all of these startup opportunities. I think this is one field where you just need a bright mind, a group of bright people come together, and there are problems waiting to be solved.
Yeah.
What are some examples of startups that you've seen either at TU Graz or elsewhere?
Yeah, you're completely right. This is sort of the time of also doing startups and start new businesses. If I look at TU Graz, and actually out of my institute, 27 startups appeared. So over the time. Not all yet exist, but this is the sort of the thing. But some of them quite successful, sold to Microsoft, for example. It's like one of those was doing aerial cameras, digital aerial cameras, and then this later on was sold. Others, like there is one successful startup in doing human retracing. You arose out of a research project. We had sort of, we men don't like to dress and retrace in shops. So the idea was you go there, take a camera, and then you try out all different clothes on you, and you see how it fits. And they made a startup out of that idea. We had some prototype at the institute. Of course, they finally developed something completely different, but this is how this developed, a successful startup. Another one was in the area of surveillance and 3D reconstructions. Have one sort of not that huge, but that does simple inspection tasks in sort of production in industry. Still doing a lot of sort of conventional computer vision because you don't have heavy compute there, so you need sort of lightweight things. Yeah, there are plenty of opportunities. And the more we talk, the more startups we find. So
let's talk a little bit about the hardware side of this whole field.
Oh yeah,
right. GPUs have changed the way we think about this whole field. Tell us a little. I'm sure you've seen a GPU as a graphics card in your computer, and today you're using it for processing. Tell us about that evolution.
Well, actually, this is a nice thing. So our institute, so where I've been, is computer vision and computer graphics together. So what we call visual computing. And when this was founded, the institute, this was sort of the strong belief that these are two fields that belong together. Because usually, if you look at other universities, they were often in different institutes. But there was a key advantage of that, and we used that. Of course, the graphics guys always knew how to program graphics cards. This is their job, rendering and blah, blah, blah. And then, so they were there, and there were no special programming languages. This was really more like assembler programming, like really there was no CUDA and then all these things that are there now. And then we had, and we just mentioned before, the optical flow. We had invented some new optical flow algorithms, but this was awfully slow to compute. This is like from one frame to another one, it was like 2, 3, 4 minutes. This is, and if you want to process a movie, and then we talked to our graphic guys sitting just next door. Could we say that? Well, of course, that there might be some possibilities. So what they did is, They wrote us all the code in front and back, what you need just to get the images on the card and do all the things. And we just had to sort of think about 4 or 5 lines of sorting more or less the differential equation. You put it there that solves you the optical flow problem. And then we put this on the graphic card, and at that time it was, instead of 3-4 minutes from frame to frame, it was I think something like 2-3 seconds. You know, and this is a game changer. Yeah? And at that time, and we used NVIDIA cards, they were there at that time. And then I gave a talk somewhere, and then NVIDIA guys saw me giving the talk and said, we will bring you over to the US for a keynote, because they saw, this might be a potential application for their cards. Wow. And they had the honor to give immediately after Jason Wang a talk about computer vision on graphic cards.
Wow.
And showing that. So this is a thing. And then, of course, from that, better programming languages arose, sure. And people saw this is useful. And then, of course, then it really took off with deep learning. But yeah, it was around, and computer vision was always looking for also hardware, because, images are hard to process, lots of data, especially when movies, you will always looking for hardware support, and the graphics cards are just the ideal thing there. Yeah?
Wonderful. Let's gaze into the crystal ball for the next 5-10 years. What are some exciting ideas that you've heard at the leading conferences that you think will be reality to touch people's lives?
Well, if you look at the application side, I think we really have talked about the applications already, and I think we will see much more.
On that, I want to go back and talk about agriculture.
Okay, yeah.
What are some ideas there that you think?
Yeah, so it's happening already now, what people call precision farming. So you take a drone, let it fly over, and then you do pesticides or nutrition just there where it's really needed. You use a robot to steer that. And of course, this is computer vision. You need the drone to detect the crops and all these things where things happen. You need the robot to steer around. I think also robotics and computer vision will have a major influence in the future. We see now deep learning and robotics coming up, and of course, a robot without sensor is useless. So we see here a lot of computer vision again coming into play. And then, of course, all these application fields, what you have. I think we also will see much more like analysis of all the data we collected of the image data to make really use of that, because at the moment, a lot of these things we're just storing. Not interpreting, and this thing in here, of course, is computer vision will help think about satellite images, think about weather, think about all these things will be influenced a lot by computer vision. Not only, but a lot. Computer vision will play a central role. In fact, I cannot imagine any application that can do without computer vision.
I'm beginning to believe that. So I have a question.
Yeah.
As a long-time computer vision scientist, in English there is a saying that says seeing is believing. Mm-hmm. Do you subscribe to that idea?
Well, we have all seen the deep fakes.
Yes, let's talk about that.
So yeah, I think it will change the way people, because as you said, when we saw an image, this was the truth. It is a picture of reality. This is no longer true. We see deepfakes, we see videos, and which are, if you look at this face generation, I have in one of my talks always you look tests like real human versus generated. Nobody can sort of guess what is computer generated, and we will see a similar development in the videos. For example, I have now created for myself an avatar. Whenever I don't have time to give greeting you, usually I would send a video over there. Now I just send a text. The avatar takes that. It can talk in any language. Nobody recognizes that. So, of course, we mark it as an avatar. But
Sure.
yeah, so yeah, this will change, but this will not happen immediately because we have been trained. This is a cultural thing, An image is something real. This will take some time till we sort of switch here.
Yeah, it's an exciting time for sure to be in this field, particularly.
Oh yeah.
Tell your closing thoughts on what you want to tell students about how to think, how to prepare for themselves, prepare themselves for careers in this
Yeah.
discipline.
The first thing I would tell any student is really do the things you're really interested in. So sort of look around, try to find exciting things, even if they might be far looking and not solvable at the moment. But if they excite you, go for it, because this is the most important thing you can do. You need to engage yourself. All these things, that we've been talking here now this last hour, they seem so easy. No, all of behind that there is a lot of work to do. You need to study, you need to have sort of the skills, but if it's in your interest, then it's not work, it's fun, because you have a goal to work on. And I think this is the most important advice I would give to a student.
Wonderful. And even in the army of computer vision engineers, so to say, there are people who are happy using existing algorithms for applications, and there are others who would be developing newer and better algorithms. What would you advise the second group of people that want to just become users of all of the technologies that you've developed and others have developed?
Well, I would also tell them, yes, but you need a basic understanding of the underlying principles.
Okay.
And this you need to study. This can be in a semester learn the basic principles, and even you want to just apply. But at the end, it pays off because you're developing better applications.
Wonderful. Professor Bischof, this has been a fascinating conversation. I learned many things, and I'm sure our listeners would end up being more knowledgeable. Thank you for making the time.
Yeah. Thank you. Thank you for inviting me. It was really fun, and fun talk to you. Thank you.
Thank you. Likewise. This is another episode of the Professor Mahesh Podcast, your resource to make informed career decisions. Until we meet again, be well, do good, and keep in touch. Goodbye.